My name is Miguel Peterson, Senior Rendering Engineer at Striking Distance Studios, and I'm here to talk about GPU Reshape and what I like to refer to as API-agnostic instrumentation and instruction-level validation. All of the work presented here is fully open source, with links provided in the end. So, modern APIs are incredibly powerful, but they're inherently complex, and the more complex something is, the more likely something is to go wrong. We typically have three questions. What went wrong? Where did it go wrong? And well, how do we even know if something went wrong? Sometimes it's easy to tell, such as a device removed, and sometimes not so easy. Now, on the CPU side, we've got excellent validation tooling, specifically the standard validation layers. However, they're rather limited by the available data. What if the issue occurs due to dynamic data only visible to the GPU? This can cause undefined behavior, crashes, or worse, nothing on your machine, but perhaps on others. In this screenshot, something's going wrong with the textual addressing. Validating things like these is what GPU Reshape is all about. So let's talk concept, and it's rather simple. Before something bad can happen, we validate it, and if something bad did happen, we report it. And really, that's all there is. Now, before I sell you on a good deal of complexity, I first want to demonstrate its ease of use. Let's say you want to launch your application from Reshape, and you want to start it with initialization validation, that is, any read has been initialized prior. Okay, so it detected an error. Let's take a closer look and let's try to figure out what resource was uninitialized. Seems it was the depth buffer. On top of this, I would like to instrument the application for resource element addressing and see if any are out of bounds. Here we go. Okay, let's take a closer look. So it seems that we are reading TAA buffer out of bounds by quite a large margin. Now, GPU Reshape offers instrumentation as a one-click endeavor immediately available without any integration. So, okay, that's where we are today. So continuing the idea, we need to figure out what can go wrong, and the answer is a lot, really. Descriptors can be bad, we can have infinite loops, we can have nans being propagated, the data can be uninitialized, we can have race conditions, etc. And we're all rather used to fighting them. To begin validating, we need to figure out what forms of validation we have. And there's quite a few of them. We can perform it statically or symbolically, but we're lacking some data, which leaves instrumentation, of which there are two, source and binary. Now, GPU Reshape being an integration-free framework doesn't really leave me with a lot of wiggle room. If all I see is binary, I have to perform binary instrumentation. Now, luckily for me, people much smarter than myself have already proved the point. GPU Reshape actually started from the paper Vulkan GPU Assisted Validation by Carl Schultz from LunaG, so we already know it's possible. And the whole idea is to take the left-hand side user code, in this case SPIR-V, and inject it with validation so it looks like the right-hand side. In this case, we're validating the coordinates of an image load instruction, and we want all of this to happen without user intervention. But it's a little bit easier to think about with source code. Again, we have an image load, and we want to validate the coordinates against the resource's dimensions, as seen on the right-hand side. If something went wrong, we report it somehow. And interestingly, many projects actually have handwritten assertion-style validation. This is fully automated through GPU Reshape. Another problem is that what if the thing we're validating can cause instability such as crashes? How do we get the data back? Then we need to guard the instruction and only execute it if validation passed. I call this safeguarding. If validation did not pass, we instead assign a dummy value to the result of the instruction. Okay. So we're beginning to get somewhere. Specifically, we're getting a lot of permutations. What I mean by this is if I was to naively instrument the binary the application provides, I'm going to end up with a lot of implementations. I'm going to have one per API, one per backend language, that is DXPC, Dixel, and SPIR-V, and anything that the future may hold. GPU Reshape attacks this problem through a custom intermediate language named GPU Reshape Intermediate Language, or GRIL for short. The basic premise is that while the backend ILs may have their differences, the concepts are mostly the same, meaning a texture sample is still a texture sample, an addition is still an addition, and so forth. So what about a common form? Specifically, I want to be able to write once and instrument everywhere. So GPU Reshape can be seen as a two-front abstraction. On one hand, we have the APIs, and on the other hand, we have GRIL and the intermediate languages behind it. Each serves as a functional abstraction for all API particularities. And to make sure I'm going in the right direction, GRIL is heavily LLVM inspired. That is, we have single static assignment, strong typing systems, functions, basic blocks, instructions, etc. All of these particularities aren't important to understand what's happening. What's most important is that all instrumentation happens on Grill. Each validation feature has exactly 0 API visibility. And Grill is essentially a common form IL that allows for bidirectional translation to and from the backend languages. On top of this, it's a native implementation, meaning it does not go through any other intermediate representations, so it's highly performant. It takes the binary IL, translates it to Grill, and then back to binary IL, and finally to the driver. But a full backend language abstraction is not the goal and would take far too long. Grill instead exposes a meaningful subset of each language, with the behavior of the unexposed constructs kept mostly the same. For example, say you modify an image load operation which has unexposed operands, and you change the coordinates of the load for whatever reason. The behavior of the unexposed operands is kept intact. And while the trivial differences in the instruction sets are abstracted away, such as address spaces differences in instruction operands, language paradigm differences are another story entirely. And two in particular, we have scalarized versus vectorized representations, and what's known as structured and unstructured control flow. What Grill does here is that it infers when it can and exposes when it cannot. And on the first paradigm difference, SPIR-V is a fully vectorized form, whereas Dixel is a scalarized form. Grill chooses to follow a fully vectorized form. It would be far more work to fully scalarize SPIR-V than to simply scalarize any changes to the Grill instructions. These snippets demonstrate what's happening. On the left-hand side, we have a vector addition, which simply gets scalarized, or rather, it gets flattened down to its individual components. And this applies to any vectorized operation. The backend, in this case the Dixel compiler, infers everything. Another difference is what's known as control flow. Now, I'm going to keep it simple and say that structured control flow is a very strict set of requirements on branching, where flow is the order of operations within a program. SPIR-V is structured, Dixel is not, and imagine Dixel as a bunch of go-tos and jumps. Thing is, inferring this is very difficult and dangerous, so it's instead exposed into the intermediate language. In this screenshot, we're performing a branch to one or two blocks, and we inform the backend where these two paths will merge later on. If the backend needs this information, it'll use it, and if not, it'll discard it. But control flow is a rather funny creature. What if a feature needs structured information? In typical HLSL, this may, for example, be a for loop or a while loop. But in ILs, it's just a bunch of basic blocks branching to each other, where we have an entry point to the loop, known as a header, and then somewhere there's a cyclical branch back, which is known as the back edge. The thing is, the backend languages may not have this information or may strip it out, so we need to reconstruct it. While this particular thing isn't very hard to reconstruct, the key is that the necessary tooling is provided to reconstruct such constructs, including loop trees, and luckily for me, there's plenty of literature on it. And a bunch of other things. We have binding models, type representations, constants, metadata, and a lot more. Now, personally, I love this stuff, but the important bit is that given compliance, translation to the backend IL is seamless. And from there, instrumentation is half the battle. The features never interact with the APIs, so that part has to be abstracted as well. Think of Reshape as a collection of building blocks. On one hand, we have a set of API abstractions, such as data streaming, descriptor management, etc. And on the other side, we have a set of standardized functionality using set abstractions. This may be commonplace Grill manipulation, analysis of shader operations, etc. There's quite a bit of stuff in here, but I briefly wanted to go over some of the things that it offers. So when it comes to validation data, we know the concept, but how do we actually get the data back from the GPU? Reshape offers a one-line Grill instruction named export that handles all of that. All memory, layout, interoperability, streaming, synchronization, etc. is automatically handled. Just call the function and the data will find its way back. Descriptor management is also one of the biggest differences between the APIs, but usually validation features just want an ID and some metadata. So enter resource tokens, providing a global ID and a little bit of metadata about it, such as the resource's type and related. This too is exposed as a one-liner through the resource token emitters that gets compiled to a single register-wise, vectorized instruction and a couple scalarized, something I'm quite happy with. And with this, most features can do their work. Another one is what I call feature programs. What if a feature wants to call their own shaders? Do we write them in HLSL, GLSL, etc.? What about just keeping the same programming models and writing the shaders entirely in Grill? This essentially allows for features to manipulate state independent of shader operations, which is a very powerful tool. And with that, we also need a lightweight command abstraction. Before any pending user operation, we may wish to inject commands such as uploading data to a pending invocation or even executing said feature programs. It's really up to the feature, anything that it needs. It can even launch their own command buffers if it so desires. So that's a lot of different things, but let's just talk about how they're used today then. So most features follow the same doctrine. We find all the instructions that can cause issues, we validate them somehow, and split up the blocks according to needs, since we may need to branch. If a fault was detected, we branch to the error block, which exports some data, and if not, we just resume the program. Pretty simple. But what about safeguarding? Well, we need an additional block, and we move the dangerous instruction to it. And in case that an error has occurred, we assign a dummy value. But to select the actual value we use, we employ these things known as phi instructions. And you can think of them as ternary operators that select the value based on the branch taken. Dummy if we came from the error block, and data if we came from the guard block. So with that doctrine, let's implement the first feature, resource bounds. It's the validation that any textual or element addressing is within bounds. This applies to buffers, structure buffers, and textures. Luckily, hardware supplies most of the functionality. We just query the resource dimensions in the shader, and if any index is larger than its size, we have an error and we export all relevant data. Other than a bit of basic block handling, this is the bulk of the work. Another feature is the validation of floating point stability. This happens on UAV writes, render target writes, and into stage data like vertices. The test itself? Well, just check if the value in any given dimensionality is either infinite or not a number. If either, we got an error. So it's nice and simple. On the descriptor side, invalid descriptors is probably the easiest way to crash the GPU. They may be undefined, subject to out-of-bounds indexing, they may have a mismatch from the compile time type to the runtime type. And maybe the table's missing entirely. Now, luckily for us, resource tokens provide all the information needed to validate things, particularly as it's a guarded operation. From this, we validate if there's a mismatch between what's expected and what's actually there. Now, there's a couple more things needed, but this is the most important bit. On top of this, to protect against crashes, we employ guarded validation. Now that we know that the descriptors are valid, what about the data inside of them? Let's validate that any read was preceded by write. Problem is, there's a lot of ways that resources can be initialized, both from command buffers and shaders. On the feature side, we basically have a very large buffer with initialization masks, which is indexed by the global ID of the resource token. One note is that today the granularity is on a per resource level. This will be greatly improved in the future. One problem though is that initializing these masks has to happen inside of a shader. If we're already inside of a shader, any user read validates the mask, and any write atomically assigns the relevant bits. But if it's happening from a command buffer write, such as a clear copy, we actually launch a separate kernel to initialize things. And it does so with feature programs. But there's another problem. What if this happens on a transfer a copy queue? I can't launch any kernels there. When reshape is enabled, these kind of queues are actually emulated. In reality, they're just a regular compute queue, even though I don't necessarily tell the application. But even if there's data, maybe it's being concurrently read and written to. So let's also try to detect that. At most, we know that there can be a single producer or multiple consumers. Currently, the granularity is between events, that is draws, dispatches, etc., and the queues that they're executed on. As with initialization, this will be greatly improved in the future. The way that this works is by assigning lock guards on writes and validating the active lock on reads. If either the lock failed on writes or something has locked the range on reads, we've got a race condition. Tracking this works the same way as initialization tracking. Basically a large buffer with the lock states indexed by the global resource ID. Each event gets a 32-bit identifier allocated to it that essentially represents the active lock. It is, however, very important to note that this is not a hazardous check. As with all other features, it reports what is actually happening. So once the descriptors are good, the data is valid, and it's probably thread safe. But sometimes there's hardware particularities, and one of these is called waterfalling. Thing is that dynamic register indexing of both S and VGPRs must be serialized. This has vast performance implications. Typically, if neither the data access, such as an array, or the indexing into set data cannot be deduced at compile time, we need to serialize this addressing. If the data is constant, we can move it to global memory. If the indexing is constant, we can try to inline the element. But what is waterfalling really? Mostly it's one of two forms. For small data types, it's a set of conditional masking instructions. While these aren't free, they're not overly expensive. But for large data types and descriptors, it compiles into an actual loop. This loop reduces the execution mask to such that each iteration only handles one unique value at a time, effectively scalarizing the loop body, and this can be very expensive. But validation of this is not easy. On the compiler side, this is resolved through a lot of optimization passes. We need to get as close as possible, so we employ what's known as conditional constant propagation, which basically figures out what can be computed at compile time. On top of this, we extend it to handle local memory operations, such as loads and stores, and simulated loops as well. Typically, this is handled in other passes, but we choose to keep it in one. And from here, the validation checks if either the data or the index may be constant folded. It's important to note that there are exceptions, such as if the indexing is uniform, but it's a very good estimate. And finally, loops. I have to note that this feature is still experimental, but it does a very good job. We want to guard against both infinite loops and TDR causing loops. The basic idea is to escape the loop before a timeout may occur. And on the CPU, we essentially have a heartbeat thread which monitors all active submissions and signals them for termination if the elapsed time exceeds any particular threshold. Grill side, each loop header, that is the entry point, is modified to atomically read a signal each iteration. If the signal is set, we escape the loop. For unstructured programs, we need to reconstruct the loop trees, which is a one-liner. Additionally, things get a little bit complicated regarding these phi instructions since there is now an additional way to escape the loop, but this is a solvable problem. All of this is functional as of today. The unsolved problem is getting CPU-fed data to a running shader. Turns out there's no specification-proof way to make this happen as of today, so we make some architectural assumptions. But the features themselves are not infallible. Take resource bounds, which queries the dimensions on descriptors. It needs valid descriptor data, otherwise it will crash the GPU. The way this is handled is through what I call hierarchical instrumentation, in that features may have dependencies on other features. In this case, resource bounds validation depends on the descriptor validation. Descriptor validation runs first, guards the instructions, then resource bounds uses the already validated descriptor data in the guarded path. This is a very convenient way to ensure the amount of work needed by each feature. And yeah, I also want to note that this is not a monolithic framework. Everything is written as plugins with the backends completely decoupled. In fact, most of the heavy lifting is done in the abstracted layer, which keeps things clean and easily shared across the different features. And while the current feature set is constrained to validation, to take one thing at a time, there are some rather exciting things in the works. And on that, I want to talk about tomorrow. Specifically, I want to be able to talk about debugging and profiling in GPU Reshape. I want to provide full-fledged in-shader debugging, but not in the typical sense. These are what I call live breakpoints, where shader execution is not stopped. Imagine, if you will, a post-processing tone mapping pass transforming color spaces, but something's wrong. You suspect one of the transformations is producing invalid data. So you hover over a variable, color in this case, and Reshape will recompile the shader within a few milliseconds and visualize exactly what that variable contains across all threads, in this case a texture. And then you turn the camera in game and the texture changes. It's live. Think of it as a live way of unboxing what the GPU is seeing at that exact moment. Another, and a staple of the CPU world, is assertions, in this case validating GGX roughness. This does require some source integration, but I think that's just fine. And what about profiling? What if we could inspect branch coherence and coverage in real time? As before, it's live. Turn the camera, play the game, watch the different branches light up. On top of this, Reshape may provide branch timings in real time to figure out where the shader is really spending its time. There are some challenges here, but I think there's a lot of really useful information. In conclusion, to me, instrumentation is not something niche. I think it has the potential to become part of everyday development. It's a rather unique way of unboxing the GPU. That said, there is a long road ahead and a bunch of features planned and ongoing stabilization efforts. But we are a fully open source collaboration. If there's any issues, proposals, general discussion, and even critique, please reach out. I will answer. And finally, I wanted to provide a genuine thanks to AMD and Avalanche and all the great people within for this collaboration, and my employer, Strike and Distance Studios, for their flexibility. Thank you.